Hello, Algebra 2. After our exploration activity, we're ready to do some formal notes on graphing absolute value functions and also to discuss transformations. And what's interesting about transformations is they're consistent across operations. So today we're looking at absolute value. Later on we'll do square roots, cube roots, cubics. All these transformations will apply the same way the rest of the year, which is pretty amazing and kind of nice. So this is your first exposure to it. Now, graphing functions of the form, and we have this kind of formula here. And what this is covering all those changes that we made to the parent graph. We added or subtracted inside next to the x, we added or subtracted outside of the absolute value, and we multiplied either by a whole number or a fraction out front. And so it covers all the possibilities. We also introduced a negative. We made a negative and saw what it did to the parent graph. Well, let's kind of let's use this formula to help us out. It turns out that the vertex of an absolute value graph that's in this format, the vertex is going to be found at HK. Now, the reason why is because if you add or subtract on the inside of the absolute value, it turns out the shift is kind of reverse of what you'd think. So they put a minus H here, but our vertex is going to be at the positive. If it was positive, it would be at the negative. But the K just moves the graph up, so our vertex is moved up K. Now, this is kind of funny. If you ignore the sign of A, if you just look at its absolute value, if the absolute value of A is greater than 1, then the graph is a vertical stretch. Now, ignoring the negative, so we say absolute value of A, that's just ignoring the negative. If the absolute value of A is less than 1, like we're talking like fractions, typical fractions, the graph is a vertical shrink. And then, of course, if A happened to be a negative number, when A is negative, the graph is reflected over the x-axis. It's flipped over. So that kind of summarizes those transformations that take place with absolute value graphs. Well, here's how we're going to put this all together. You're going to be asked to graph absolute value functions, and the way we're going to do it is going to be similar to how you graph parabolas. And it's been a while probably since you graphed a parabola. So let me explain how you're going to do it. You're going to start off. We're basically going to do kind of a two-step process here. You're going to start off and you're going to plot the axis of symmetry and the vertex, which again, if you're looking at this format, your vertex is going to be at HK. After you've plotted the axis of symmetry, remember that's that line of symmetry down the middle. You make it dashed because it's not actually coordinates on your graph, but it's the middle of your graph and it's symmetric across it. But after you plot the axis of symmetry and your vertex, then you will make a table. Using two x values to the left or 2 x values to the right. Of the vertex. So you're going to make a table using 2 x values to the left or 2 x values to the right of the vertex. Now, the reason you're going to do that is basically, I'll just kind of make a little sketch here. So you get your vertex, which gets you your axis of symmetry. Then when you make your table and you get 2 more points, either to the left or to the right, you can then reflect them over across your axis of symmetry, and boom, you've got a graph and you're all done. So let's put this into action. For our first one, we've got f of x equals 2 times the absolute value of x. Well, start off, what's your vertex? Well, since nothing's being added or subtracted on the inside, nothing's being added or subtracted on the outside, your vertex is just going to be at the origin, 0, 0. Step 2, make a table. Well, I guess before I do that, let's go ahead and go consult our graph here. Our vertex is at 0, 0, and that means our axis of symmetry is the y-axis. So there's my little dashed line representing my axis of symmetry or line of symmetry. And then I want to use 2 x values to the right or 2 x values to the left of the vertex. So since I'm at 0, I'm going to use 1 and 2. And then we evaluate for the y values. So it's going to be 2 times the absolute value of 1. The absolute value of 1 is 1. 1 times 2 is 2. 2 times the absolute value of 2. Well, the absolute value of 2 is 2 times 2 is 4. So we go 1, 2, 2, 4, and that gives us half of our graph. To get the other half of our graph, we reflect them over. So I'm 2 away, so I'll go 2 away on the other side, make a dot. The graph paper's kind of light there, but I kind of like it. You can see your graph a little better. And there you go, you've graphed your absolute value graph right there. Now, just a heads up, I need to keep talking about domain and range, reminding you because it's going to be something mandated here pretty soon. Your domain would be all real numbers because all x values are going to be counted. Okay, this goes to the left forever, goes to the right forever. But your range would not be all real numbers. Basically, it would be 0 up. Okay, 0 up. So I would say y is greater than or equal to 0 for my range, 0 up. All right, let's move on to our next example here. Our vertex, that's where you start out. Our vertex is going to be 0 again for the x, and now a 2. I go 0, 2, make my dot. My axis of symmetry is right down the middle again. And then I make my table. And I want to show you can use, positives or negatives. It doesn't matter, left side or right side of the graph. You're still going to get the same thing. So just for kicks, I'm going to use -1 and -2. So that's 2 x values to the left. Plug it in and take your time on this, okay? You do order of operations. You start inside here. This is a grouping symbol. So what's the absolute value of -1? It's 1. But then I got a negative on the outside. So I've got -1 plus 2, which is 1. Negative, absolute value -2 plus 2. Step by step here. Absolute value of -2 is 2, but then I slap a negative on it. And -2 plus 2 is 0. Plot those points. -1. 1. Sorry, I paused there for a second. Negative 1, 1. Negative 2, 0. Reflect them across your line of symmetry. And that is a pretty good looking absolute value graph. The domain on this, again, would be all real numbers, no restrictions on your x's that you use, but your range in this case would be y values that are less than or equal to 2. All right, let's flip it over, see what else we got here. A little more complicated. We still start out with our vertex. Now our vertex, remember, it's going to be the opposite. So it's going to be 2, 1. So we go 2, 1, make a dot. Now we can see our line of symmetry a little more because it's off of the y-axis there. And then I get 2 more points, 2 more coordinates to the right or to the left. So I want to go to the left because that'll be 1 and 0. Those seem easier to me. Again, it doesn't matter which way you go. It'll end up when you reflect it across, it'll be the same. And then take your time with this. 3 absolute value 1 minus 2 plus 1. So 1 minus 2, remember you simplify the inside first. 1 minus 2 is negative 1. But then the absolute value of negative 1 is 1. 1 times 3. So we get 3 plus 1, which is 4. Let's do 0. 3. Absolute value 0 minus 2 plus 1. 0 minus 2 is negative 2. Absolute value of negative 2 is 2. 2 times 3 is 6 plus 1 is 7. So we go 1 up 4 and 0 up 7. So it's about right there. I know I go off the graph a little bit, but that's okay. And then we reflect them over. So 1 to the left is now 1 to the right. 2 to the left is now 2 to the right. And we have ourselves a pretty nice absolute value graph. The domain, still all real numbers. The range, since it's going up, we're going to say y is greater than or equal to 1. Our lowest point is 1 there. And notice that 3 out there, that's a vertical stretch. This is a little bit stretched out. It appears narrower. It's not in actuality narrower, but it opens up a little narrower. But yeah, it's a vertical stretch, so that's interesting. All right, let's try another one. Vertex. Opposite, negative 3. Same, negative 2. So we go negative 3, negative 2, make our dot, draw our axis of symmetry. And now I want to use 2 points. And I'm going to use, to make it easier, I'm going to go to the right. So I'm going to use negative 2 and negative 1. And carefully figure this out. Negative 2 plus 3, you want to simplify that first. Negative 2 plus 3 is 1. Absolute value of 1 is 1. 1 minus 2 is negative 1. Absolute value, negative 1 plus 3. So negative 1 plus 3 is 2. Absolute value of 2 is 2. 2 minus 2 is 0. So we go negative 2, negative 1, negative 1, 0. Reflect those across your line of symmetry there. And there we have it. And domain, all real numbers. Range, it's going up, so we say y is greater than or equal to negative 2. All right, so now we're going to switch gears just a little bit. We're going to go backwards, okay? We're going to write absolute value functions from a graph, which is pretty cool. The first thing you're going to do is you're going to find the vertex, because that kind of gives you the soul of your absolute value function, okay? So you're going to find the vertex. That'll be half the battle right there, because your vertex tells you these components of your equation. But then the next thing is you always have some A value out front. So what you're going to do is you're going to solve for A. And you're going to do it using any other point on the graph. Now you can't use the vertex, that'll mess it up. You can't use the vertex. You got to use any other point on the graph. So let's put this into action here. So we're going backwards. Well, we've got on our graph here, we've got our vertex. Our vertex appears to be at 3, 1. And like I said, that's going to give us most of our equation right there. So from there, we can go ahead and write y equals a. I don't know what a is just yet, but I know that's going to be x minus 3, close the absolute value, plus 1. And I just need to figure out what a is. And to do that, I'm going to get another coordinate. So I'm looking at my graph, and I want to get a good coordinate. And that one's just staring at me right there, 5, 5. I'm going to temporarily use that to help me solve for a. So we're going to use 5, 5 to help me solve for a. So 5 minus 3 is 2. Absolute value of 2 is 2. 2 times a is 2a. And then I solve this by subtracting a 1 to get 4, dividing by 2 to get 2. So now that I've solved for a, I'm going to rewrite this. Y equals 2. Absolute value, x minus 3 plus 1. Now, this technique that we're using, where we use an extra coordinate to help us solve for an unknown, is going to be very common throughout the year. And it's also used when you try to use a slope-intercept form to write the equation of a line. From the very beginning, you got to solve for b and then rewrite it. So there you have it. Let's go on to one more. Our vertex is at -2, 3. So I can start writing my equation. I don't know what my a value is, but I know it's going to be x plus 2 in the absolute value bracket and plus 3. Now I need one other coordinate, one other place. Oh man, there's tons of them. I'm going to use right there. I'm going to use 0, 1. I like to use 0. It usually makes things easier. But I'm going to use 0, 1 to help me solve for a. So, whoops, put a 1 in there. I'm going to help solve for a. X is 0. 0 plus 2 is 2. Absolute value of 2 is 2. 2 times a is what we're left with there. Subtract that 3 over, you'll get -2. Divide by 2, and a is equal to a -1. So when you rewrite this, you're going to write y equals -1, absolute value, x plus 2 plus 3. Now, in reality, you don't have to put the 1 there. You can just put a negative. But I think that's a pretty darn good equation right there. So listen, ladies and gentlemen, this is some new stuff. You're going to want to practice it. So there's the practice right there. Thanks so much for watching.